Okay, so I'm just gonna, in this video, go over an epsilon-delta proof of a limit with the understanding that I know that not everyone in this class has taken real analysis, and so we're not going to worry too much about these things, and you'll learn more of them when you take 4300. Um, but this idea is important to see. At least it's important to see that when you do get to real analysis, that really the only thing that you need uh, to do these epsilon delta proofs is really a notion of a distance or a metric. And we have that in complex numbers. So that's why we're going to do this example, with the understanding that I'm never going to ask you to do an example like this. Okay, so what we'd like to do in this example is compute the limit as z approaches 1 plus I of the function 2 plus iz. Now this is a fantastic function. It's in fact a linear function, an honest linear function, not even affine, linear on the nose. And linear functions are continuous. What does that mean? It means that we can just plug in the value. Okay, so we plug in the value, we do our complex arithmetic. I think what we're going to get when we do this is something like 1 plus 3i, because we'll get a 2 and then a negative 1, and the cross terms 2 plus 1 is 3. Great. Fantastic. Now, the rule will be in this class, if you can just plug it in, just plug it in, and we can. Nevertheless, let's do the actual proof. Okay, so this is relying on continuity to be able to do this. So really we're using that 2 plus iz is continuous, which is something that was never proven, but we will get to that when we get to that. So let's do our epsilon delta proof. So what we do with an epsilon delta proof is we try to make the distance in outputs small. So 2 plus iz minus 1 plus 3i, we want to make this small. So we want to make this guy small. And the way in which we do that is we play around with inequalities. And let me just notice here that we can kind of factor out a 2 plus I from both terms. In fact, 1 plus 3i is 2 plus I times 1 plus I, because that's what we did. So we can sort of factor out a 2 plus I, and we pull out our, let me not put too many associations. When we pull out our 2 plus I from both terms, actually we know that modulus behaves well with respect to multiplication, so we can just write that modulus on the outside. All right, now we can compute the modulus of 2 plus I. I believe it's root 5. And now we insert our deltas. So what we want to do is we want to pick delta to be epsilon over root 5. Then, provided the distance between z and 1 plus I is close enough, we know that the distance in outputs is going to be equal to root 5 times z minus 1 plus I. We know that's going to be true. But if I'm close enough to 1 plus I know my distance in outputs will be close enough to 1 plus 3i. So we're going to replace now our modulus expression with a less than sign, and we're going to put in epsilon over root 5. We're going to put in our delta. Let me do that in steps, actually. Sorry. That's going to be less than root 5 times delta, because we're supposing that we're pretty close to 1 plus I. And that's root 5 times epsilon over root 5, which is epsilon. Okay, so no matter how close you want to be in outputs, so you pick your closeness parameter epsilon, as long as your inputs are epsilon over root 5, or within epsilon over root 5 from 1 plus I, our outputs will be that closeness parameter. Okay. So anyways, that is the bones of an epsilon delta proof. We didn't write it super formally. But that's the idea of how it works. You create your difference of inputs somewhere within your difference of outputs expression. And sometimes these are actually quite complicated. With linear functions, they're very simple, but these can get very complicated, and we've arrived at the result.